Okay, looks like we are just about there on the live event. I'm gonna paste that into the chat here. Had the wrong link before, so the new link is in Google Classroom. I'll go ahead and paste that into the chat here. Okay, that should go a little bit better here. Alright, and just a sec, I am going to mute myself on the Google Meet, and I am going to get this going here so you guys don't start hearing double. So just a sec. There we go, just muted myself, and we will go ahead and get underway here. So just a sec, and we'll go ahead and pull up some FRQ. So today, kind of my goal is to get a look at some of the things you can expect on the actual stats exam, and get some questions and answers, kind of get a little bit more comfortable with what might be in here. So let's go ahead and get this going here. All right. So this first problem is one that was made for some practice-free response for this. So, real estate analyst is studying housing trends in two large cities, Primeville and Thunder City. One measure the analyst plans to compare is the sale price of homes in the two cities over the past 12 months. To gather data, the analyst uses a public website to collect random samples of sale prices in each city. 50 homes sold in Primeville and 100 homes sold in Thunder City make up each sample. The data are shown in the dot plots below, with the sale price shown in thousands of dollars. So I'm going to play with this for just a sec to make the layout work a little bit better for us. And let's see here, going to... There we go, so now I can type along the side there. And feel free to drop questions into the chat here. I am not going to be actively monitoring the chat on the YouTube link, so the place to be is going to be the Google Meets here. All right, so let's get this going. First things first, it's asking us to compare the distribution of housing sale prices from Primeville and Thunder City. So anytime it asks us to compare or describe, that is where we want to have that Pavlovian response of shape center spread. So for part A, I'm going to put this in red here. There we go. For part A, we are going to be looking for shape center spread for both of those. So it is really hard to read that on the screen. So here, this is thousands of dollars, and that kind of middle section there is $400,000. So we can see that both distributions have a center near $400,000. and both are roughly symmetric. So we've got center, we've got shape. We need to discuss the spread. So with this one, generally we're going to be looking at something like the standard deviation, or we're going to be looking at interquartile range. With this one, it would be a pain to actually, it would be theoretically possible, but a pain to get the interquartile range or anything like that. So we're going to be looking at the overall range as a measure of spread here. So we would say the distribution of sale prices in Primeville is less variable than that of Thunder City. And looking at this, we've got a range. It goes from about 250,000 here to about 500,000. So the range in Primeville is approximately $300,000. And in Thunder City, that range is going to be approximately, so that goes from 200,000 to 600,000, so that would be approximately $400,000. So there we've got shape, center, and spread for that one. I'm going to drop the size down here a little bit so we can get a little bit more on the screen here. So, part B, we are looking at one home is selected at random from those analyst samples. What is the probability that the home selected sold for over $500,000? So for that one, we are going to be looking at how many homes in all of this sold for more than $500,000, and we want to take that out of the total number of homes that we were looking at. So this is quite literally going to be a matter of counting here. So if we look, we've got excuse me, I'm going to actually start at 500,000, answer the question that's being asked. So we have 1 here, 2, 3, 4, 5, 6, 7, 8, 9. So the probability that X is more than $500,000. Wow, this is just very big type. Let's try something a little bit smaller. And okay. So that probability is going to be 9 from both of those there. Out of, we are told that there are 50 homes in Primeville and 100 homes in Thunder City for the sample. So that's a total of 150. You can keep things as fractions, but if you like, you can simplify or change that to a decimal. So the probability there would be 0.06. Pretty small probability there. Okay, going to try and give myself a little bit more space here, and let's change that font size down a little bit. And this is a good time to check for readability, to check for audio quality coming through. So if there's any issue that you're experiencing with the YouTube feed, please let me know in the chat here. I'll see what I can do to fix that. Alright, so that was part 1 of problem B, and part 2 asks us to look at, given that the home selected was sold in Primeville, what is the probability that the home sold for over $500,000? So this is looking at the conditional probability of just this set right here. So for that one, we are going to be looking at the probability that X is more than 500,000 given that the home is in Primeville. So we've only got 2 homes in Primeville that are over $500,000, and we've got a sample size of 50 from Primeville. So that's going to be 2 over 50, or that would be 0.04. Let me see if I can make that show up a little bit better. And nope, that's how we're doing it, huh? That's unfortunate. Let's try here. There we go. It's a little bit smaller, but it shows up there. So right now, just let me know in the chat if there are any questions so far, anything that you'd like to take a closer look at. All right, so part C is asking us, this is getting a deep dive into probability, which is kind of nice because that's one of the topics I want to make sure we reviewed today. Among the homes in the analyst samples, are the events sold in Primeville and sale price over $500,000 independent? Explain your response. So this one is making sure that we understand what it means for probability events to be independent. So if they are independent, then the conditional probability and the general probability should be the same. So because in this case these two are not equal, the probability of a home being sold for more than 500,000 given that it's in Primeville is going to tell us that that formatting got wacky there. All right, don't like that either. There we go. So because that conditional probability is not equal to the probability without the conditional there, those events are not independent. Let's see. All right, that gets us through part C. And we're going to look at the end of this. There's a lot to this one. So the second part of this, we are looking at carrying on with what we have here. So using technology, the analyst computes a 90% confidence interval for the difference in mean sale price between the two cities. The interval is given by negative 18.997 to 19.397. And we need to interpret the meaning of 90% confidence in this context. So what this means for us, I'm going to surf down here a little bit. What this winds up meaning for us is that 90% confidence means that the procedure used to generate the confidence interval for the difference in mean sale price will capture the true difference 90% of the time. Based on that confidence interval, we do not have convincing evidence that they are different because 0 is included in that interval. So because that interval includes 0, we can't say with confidence that 0 isn't part of that interval. So we don't have evidence of a significant difference there. All right, anything from that folks want to look at, discuss, think about, anything, anybody? All right, we'll go ahead and march on to another kind of sample problem. So here we go. So this one is looking at the effects of distraction on completing simple tasks. Not going to lie, working during this time with 2 kids in the house and interruptions has made this become very relevant for me. So we are going to be looking at a sample of 20 students. They're doing a cup stacking task, and they are evaluated twice. One trial is completed in a quiet room, and the second trial is completed in a room where 10 students were paid to cheer loudly for the participant as they stacked the cups. A coin was flipped to determine which trial the student would complete first. After completing their initial trial, the student then moved to a new room to complete the other trial. For each trial, the time required to complete the task was recorded. So the first thing that we need to do here is explain why it is necessary for the researcher to randomize the order of the trials for each student. So, looking at this, okay, that is tiny and not helpful. Okay. Let's try this again. There we go. So, without random assignment, the order in which participants did the trials could have an effect on their speed. Specifically, the second trial, during the second trial, participants have already completed the task before. And may improve their time. Randomizing the order mitigates or evens out the effects of experience or other potentially confounding variables. Is this an observational study or an experiment? Because subjects were assigned which task would be completed, which task they would complete first. This is an experiment. And here we get to see that they like mixing in a bunch of different topics all in one thing. So for each student, a coin is flipped to determine which trial is completed first. What is the probability that the researcher does not see the first tail until the 6th coin flip? So this is a scenario that can be described with a geometric distribution. There is a fixed probability of tails for each trial. The trials are independent, and we are interested in how long it takes to see the first tails. So, that probability would be probability x equals 6 is going to be the probability that we have exactly 5 failures, followed by 1 success. And if you notice, that is going to be the same as 0.5 to the 6th power, which would be that lovely decimal right there. I'll pause for questions before moving on to analyzing the box plots here. All right. This box plots for each of the 20 students, the time required to complete the task both in the quiet room and the loud room is shown in the box plots. In addition, the difference between the task completion times between the 2 rooms for each student is given in a box plot. So we're going to go ahead and put this in. Okay, why is there a gap there? There we are. So the researcher claims that on average, students will complete the quiet room task in less time than the loud room. State the null and alternative hypothesis the researcher should use to test the claim. Make sure to define any parameters you use. So for part D here, we are going to let the mu sub L be the mean time for the loud room. We're going to let mu sub Q be the mean time for the quiet room. And I really should have paid attention to that because those were useless to define. Go me. So actually, because this is asking about the difference, we are going to instead be dealing with mu L minus Q, which is going to equal the mean difference in time between the loud and quiet room. Expanded to all people. And let me hedge my bets here because statistics is nothing if not about hedging your bets. So really for all comparable groups of people. There we go, that sounds like a good enough hedge for me there. So with that, our null hypothesis is that is that the mean of L minus Q is 0. Our alternative hypothesis, our H sub A, would then be that our mean of loud minus quiet is greater than 0. And that's cute. Why are you slipping down there? Okay, neat. So we've got our null alternative hypotheses there, and we are going to be having to name the kind of inference that will be done. So just a sec here. So for part E, the researcher should use a matched pairs t-test to find the mean. And really, matched pairs is a special case of a one-sample t-test. For the conditions, we need to have 3 things. First, is this random? And we are told that students were randomly assigned to the treatment groups. Or in this case, the treatment groups are which trial did they do first. So students were randomly assigned which room they were in first. The second condition that we need is that they are all independent. And this condition of independence is the 10% condition. So there are at least 200 similar students in the population of interest. This is a reasonable assumption. The last is the normal approximation. And if we look, the box plot up there is roughly symmetric. So we would expect that with the sample size that we have, a sample size of 20, that should be sufficient to guarantee an approximately normal distribution. All right, part F, the last bit of this one, is asking us, based on this p-value, what should the researcher conclude? So notice that in this question, they didn't ask you to calculate the t-test. They didn't actually ask you to perform that test. They're asking you to interpret it, though. This is based on the information we've received from the College Board, most likely going to be the kind of task that you're asked to do. So you're not going to have to do the detailed calculations of p-values and t's and look things up with degrees of freedom and do that. And they are technically making it so that you shouldn't have to use a graphing calculator. That being said, have it on hand, be prepared to use it, but realize that they're designing this so that you don't have to. So they give us a p-value, so they're not as concerned with can you crunch the numbers as can you interpret this. So that p-value is very small. So based on a small p-value like that, we would conclude that there is a statistically significant difference. Because the p-value represents the probability that a sample with a mean with, there we go, with a mean x bar of L minus Q or larger will be drawn from a population where mu of L minus Q equals 0. This suggests that the null hypothesis is unlikely to be true. With a probability this small, we can safely reject the null hypothesis and conclude that students will complete the quiet room task in less time than the loud room task. And there we have it. The cup stacking problem. I just want to pause for a sec and see if we want to do one more of these, or if we want to hit something a little bit more topic specific for our last practice problem here. Alright, I'm going to go ahead and get one more problem up for us. And this one is kind of nice because it gets us a chance for practicing with least squares regression and residual plots. So this will hopefully help us out here. One thing that I do want to make sure I deal with before we get to the next problem. Some things to watch out for. In the problem that we just did, the trap that is easy to fall into is the matched pairs versus two sample. Because each participant did both things, that's going to be matched pairs. The temptation is often to do two sample for something like this, and you want to check and see, are we in fact taking two samples, or are we getting two sets of data from one sample? So that's the thing to be aware of. And let's take a look at the last problem for today here. And, oh, classy, Mr. Turner, classy. You kept the PDF there. So there we go. Trim that a little bit better. So for this last problem, researcher is looking at BMI and blood pressure, and I'm going to try and fix this really quick. There we go, give myself as much room as possible. And we'll do text wrapping here. Okay, so the first question, because of financial constraints, it was based on a convenient sample of students training for sports at the athletic facility. Why might such a sampling method lead to a biased estimate of the mean resting systolic blood pressure for all students attending the university? So, because the convenient sample took students training for sports, it is likely that they will be more physically active than the student population at large. Therefore, this sample will likely show a lower systolic blood pressure than we would get from a random sample. All right, so what we've got here, another thing to look out for, they are giving us a residual plot and the LSRL. This plot that is showing is not the plot of the data. So that is a thing to be aware of and be mindful of. But we do have the information about the LSRL. So in this one, the slope of the LSRL, that is going to be over in the computer printout, and it's going to be the predictor that actually gives a variable. So we're going to look at the predictor BMI, and then coef, the coefficient, is going to be the one that we can use there. So the coefficient for the BMI would be 1.647, and the slope interpreted in context. This means for every increase of 1 in BMI, the model predicts that systolic pressure, blood pressure, will increase by 1.647 units. All right. Next, it's asking if a linear model is appropriate for the data and to explain the reasoning. So looking at this data, what we can see, the place to look for whether a linear model is appropriate or not is going to be on the residual plot, and we are looking for, is there a pattern? So looking here, we see that points are scattered above and below 0. We don't have as much data out at the high end of BMI, but where we do, the plot does appear to be random. So because the residual plot shows a reasonably random scatter of points above and below 0, it appears that a linear model is appropriate in this circumstance. Looking at the R squared, 25.3% R squared is not great. So what this shows here is that this model, although it's appropriate, it's not got great predictive power. So that's what's going on there. Let's go ahead and look at the last two questions here, and it'll take just a sec to get this pulled up and brought over. So let's do this. And there we are. So, one student in the sample had a BMI of 18.5. Estimate the resting systolic pressure reading for this student recorded by the researcher. So here we're going to assume that the model is accurate and helpful here. So the model predicts that we will call this okay, let's try this again. So our predicted systolic is going to be 90.051 plus 1.647 times the BMI. So in that case, the BMI that we're dealing with is 18.5. And if you give me just a second to approximate what that is going to be, that BMI with that blood pressure, that should be, if I have done my math correctly, 116.0205. So that's what we'd expect for the predicted systolic blood pressure. And let's see. Okay. Hold on just a second. Oh! Okay, so, my bad. I got a little bit ahead of myself there. So let me calculate that again, and let's give this a try. Okay, so the predicted systolic is 120 and change. And if we look at the plot here, so the BMI of 18.5, there's just one student who has that BMI there, and I am going to see if I can actually show. There we go. Let's see here. So I'm going to highlight that dot. So that right there is the point that we're interested in. So that BMI of 18.5 corresponds to a residual of, looks like it's approximately negative 4.5. So this question isn't asking what the model predicts, but this is asking us to estimate what was actually recorded here. So that residual of negative 4.5 is telling us that the real reading was about 4.5 units below what was predicted. So So we can estimate that the researcher recorded a blood pressure of approximately 116. All right, getting ahead to part E here. Let's go ahead and move that up. The researcher claims that the proportion of students at the university who have high blood pressure is greater than the national proportion of adults of similar age who have high blood pressure, which is estimated to be 35%. To test this claim, the researcher takes a random sample of 200 students and measures the resting systolic blood pressure for each student. So for this one, we're looking at proportions, so we know we're going to be doing a z-test of some kind. And because we are comparing this against an estimate and not something where we have a sample with actual data, we are going to be doing a one-sample z-test. So not a one-sample, a one-proportion z-test. Excuse me. A one-proportion z-test will be an appropriate inference for this situation. We need to verify that the conditions have been met. So, first condition is always random. We are told a random sample of 200 students will be collected. Next is independent. And remember, this is our 10% condition. There we go. So we can assume that there are at least 2,000 college students in the population of interest, that our sample size is less than 10% of the population. And then our last condition is that it is approximately normal. So this is going to be the NP greater than 5. So here, n times, remember that this is our population from the our proportion from the null hypothesis. So our null hypothesis is that it'll be 35%. So that's going to be 200 times 35%, which is going to be 70. And the other thing that we need to check is that n times 1 minus p naught is also greater than 10. So that's going to be 200 times 0.65. So that's going to be 130. So both are at least 10. I'm going to give a sec for the video to catch up to where we are and break for questions here. Alright, I'll go ahead and end the stream and unmute myself from this.